The topic of discussion is stages of oogenesis and its regulation. The primordial germ cell or oogonia migrate from the yolk sac of embryo to the genital ridge at about 6th week of gestation. So it comes and to the genital ridge at about 6th week of gestation. The oogonia undergoes many mitotic divisions, and the number of oogonia reaches after the mitotic division, it is around 7 million. And so when the mitosis ceases, the oogonia are called oocytes, and the follicle that contains this oogonia, they are denoted as the primary oocyte. And in humans, no new ova are formed after birth. So these are the oogonia which are undergoing so many mitotic divisions, and after the end of this mitotic process, the total number of primary oocyte or primordial follicle will be 7 million. A baby during fetal life gains around 7 million primordial follicle. No new ova are formed after birth. Now, how these primordial follicles, they ultimately form the mature ova at the time of puberty, that is our point of interest. Although the 7 million primordial follicle are developed in fetal life, many of them undergo atresia or involution. Hence, at the time of birth, there are 2 million of ova. So, initially it was 7 million. So, at the time of birth, it is 2 million, and 50% of it remains atresic. That's why the active number of ova, it is around 1 million. And this 1 million, out of this 1 million, those who are normal, they enter into the first meiotic division at this time, and at the first meiotic division, they come to an arrest at the prophase 1. So no new ova after birth, and 7 million primordial follicle develop during fetal stage. Many of them undergo atresia at the time of birth. Its number is 2 million. 50% of it are atretic, so active form is 1 million, and this 1 million, they will enter into the meiosis 1 and will be arrested at prophase 1. So now we want to know the follicular basis of meiotic arrest at diprotein stage of prophase. So it is said that the intraoocyte elevated CAMP is responsible for this meiotic arrest. So from this schematic depiction, we can say that this is G protein coupled receptor. It is G stimulatory protein. This is coupled with adenyl cyclase. We know that it can convert ATP to CAMP. Now this CAMP will generate the protein kinase A. So it is a kinase protein. That means it can cause phosphorylation of so many intracellular proteins. Among this intracellular protein, one important protein is the CDK1 and cyclin B complex. The phosphorylation of this complex will result in the meiotic arrest. So this is the picture of a diprotein arrested oocyte. You can see that the central portion of it is a primary oocyte, and the surrounding this oocyte there is the flattened granulosa cell, and this oocyte and the granulosa cell as a whole it is forming the basic unit of the ovary, that is primordial follicle. Now our question is, how long this meiotic arrest will persist? So this arrest will continue up to puberty. So the fetus, in the fetus there are 7 million primordial follicle. At the time of birth, 2 million follicle. Out of it, 1 million are active. So these 1 million, they will remain at a quiescent, a silent or atretic state until and unless the puberty is reached. Now during the silent or quiescent phase also, the atresia of ovary continues. So at the time of ovary, the ultimate number of ova or primordial follicle that will remain, it is 3 lakh. So this is our primordial follicle, and this is the only follicle present before puberty. So when the puberty is achieved, these 20 to 30 of these primordial follicles from each cycle, they will enter into the process of maturation. And out of this 20 to 30, there will be one follicle that will start to grow rapidly and ultimately reach the level of this final Graafian follicle level. And this will undergo ovulation. And this particular follicle, which is growing rapidly and attaining the ultimate level of Graafian follicle, is denoted as the dominant follicle. It is uncertain how one follicle is selected to be dominant follicle, but it seems to be related to the ability of the follicle to secrete estrogen inside it. Now, what are the stages of maturation? So from the primordial follicle, they will move on to primary follicle. From the primary follicle, they will so this is your primary follicle. Then they will form the early preantral, then the preantral, then the antral or matured or the Graafian follicle. These are the stages of maturation. So, and we know that from the primordial follicle, few of them, they will enter into the maturation process, will form the primary follicle, and some of them will undergo regression by the process of apoptosis. So this is the ova. This is the ovary containing follicle at different stages of maturation, and this is the ovary containing all these follicles at different stages of maturation. But we know that only one of this ova per cycle, it is released in ovulation. So if the reproduction age group of a female, suppose it starts from 13 years and it goes up to 45 years. So this is total the reproductive age group. So we are getting total 500 cycles. So each cycle will get 1 ova. So throughout the whole reproductive life, the course of whole reproduction life, only 500 of this follicle will be utilized. We know that even after atresia, at the time of puberty, the stored number of follicles was 3 lakh, and out of them only 500 will be used in the course of whole normal reproduction life. Now we want to focus on two things. One is the process of maturation. How this primordial follicle, when it is entering in the process of maturation, what are the steps by which it is achieving the highest goal of Graafian follicle? This is number one. And number two, after maturation, after attaining the level of Graafian follicle, how it is released from the ovary. So these two is our point of interest. So from the primordial follicle, which is the only follicle present before puberty, we know that 20 to 30 of them, they will enter into the process of maturation. And in this process of maturation, actually the change will take place into 3 areas. One is the area of the central oocyte. This will undergo change. Second is the outer follicular cell or the granulosa cell. So the changes will happen at the granulosa cell, and third at the surrounding stromal cell. So the maturation process means the gradual changes of oocyte, of follicular or granulosa cells, and the surrounding stromal cell. So before going to the histology, we want to see what are the changes of size happening in these follicles. So the size of the primordial follicle, it is around 40 micrometer, and the central oocyte, it is around 25 to 30 micrometer.
In my primary follicle, the size is 100 micrometer and the oocyte is 50 micrometer. The secondary follicle, it is 200 micrometer and the central oocyte is 80 micrometer. And the antral follicle, it is 400 micrometer and oocyte is 80 micrometer. And it is said that when this matured follicle, it will attain a diameter of 10 millimeter. That means it has achieved its final level. It is a time for ovulation now. So this is the maximum level it can achieve. After that, there will be ovulation. Now come to the histological changes. In the primary follicle, you can see at the central part, we have the primary oocyte. That oocyte which is arrested in the diplotin phase of prophase. And surrounding this oocyte, there is one layer. This layer is your zona pellucida. This zona pellucida is secreted by the oocyte and it lies in between oocyte and the granulosa cell. Beyond this zona pellucida, we have the granulosa cell layer. This granulosa cell layer, it is separated from the outside stromal layer by the basement membrane. So this is your basement membrane layer. And these granulosa cells, they have FSH receptors in them. Outside this basal lamina or basement membrane, we have the theca cells, which is further divided into theca externa and theca interna. Theca interna, it has got the LH receptors in it. Now what happens during the process of maturation, there will be appearance of some spaces in between the granulosa cells. These spaces are denoted as the antrum, and the antral fluid will be secreted among these spaces. So in the antral follicle you will find, so we have the oocyte, surrounding the oocyte we have the zona pellucida, surrounding the zona pellucida we have the granulosa cells. Now these granulosa cells, they are distributed into two parts. One is the granulosa cell that is forming the wall of the follicle, so this part. And another particular type of granulosa cell which is specially covering the oocyte. Now this specially covering oocyte part is our corona radiata. And the corona radiata and the granulosa cell, where it is connected with the larger mass of the granulosa cell, so this part will be denoted as the cumulus oophorus. So this, from this picture, it is well depicted. The central oocyte and the granulosa cell surrounding it is our corona radiata, and they are connected with the major granulosa mass with the cumulus oophorus. This is the antrum containing the antral fluid. So now it is a stage of final Graafian follicle where the follicular antrum enlarges, oocyte lies eccentrically in the follicle, and most importantly, the first meiotic division arrest, it is withdrawn and the meiotic division is complete. Just before ovulation, the first meiotic division is completed. One of the daughter cells, the secondary oocyte, will receive most of the cytoplasm, while the other, the first polar body, will undergo fragmentation and it will disappear, and the secondary oocyte immediately enters into the second meiotic division. But again another arrest. There will be stoppage of the meiosis 2 at the level of metaphase. So from here we can see that the meiosis was remained arrest since the birth up to the puberty. This was a phase of silence, and at the time of puberty, just before ovulation, the meiosis, it is completed. The arrest is withdrawn, and when the arrest is withdrawn, and there is development of the secondary oocyte. This secondary oocyte will again enter into the meiosis 2 and it will be arrested again into the metaphase. And we know that this is our primary oocyte which was arrested at the prophase level. It was meiotic division, so it is 46x. So when the arrest is withdrawn, the meiosis is complete. It will form the secondary oocyte, which contains a 23X, and one first polar body will be also formed. And this secondary oocyte, now it will try to form the haploid ovum, and for this reason it will enter into the meiosis 2, and again this meiosis 2 will be arrested at the level of metaphase. Now we want to know two things. One is that after this uh, formation of secondary oocyte, the secondary oocyte will undergo ovulation. It will be taken up by the uh, fallopian tube fimbria, and we want to know how long this second arrest will persist. So within the fallopian tube, if this ovum, if this secondary oocyte is fertilized by the sperm, this fertilization can only withdraw the arrest of the second meiosis. If there is no fertilization, it will pass through the uterus and it will come out through the vagina. But only and only if there is fertilization, then this meiosis arrest will be withdrawn. So there will be formation of the haploid ovum, and this haploid ovum will combine with the haploid sperm, and the zygote will be formed. So we know now the process of meiosis arrest, what has happened at the prophase 1. The mechanism we already discussed, that it is due to the intraoocyte elevated level of CAMP, and the CAMP is synthesized and the degradation of CAMP is also prevented. All these are the results. Now we want to know what actually is happening. Who was this magic man or magic incidence that is withdrawing this arrest just before ovulation? And our second question is also, so when the metaphase arrest is there, I told you that the fertilization will withdraw this arrest. So what actually fertilization does so that the arrest is withdrawn? So I want to give the second answer first. The arrest in the metaphase is due, at least in some species, due to the formation of the ovum, formation in the ovum, the protein pp39MOS. This is encoded by a CMOS proto-oncogene. When the fertilization occurs, it is seen that this pp39MOS, it is destroyed within 30 minutes by a protein that is known as calpain. This protein is known as calpain, and this calpain protein is a calcium dependent cysteine protein. So we can say here there is calpain protein, which is actually causing the withdrawal of arrest in the metaphase 2 after fertilization. Now come to the question number 1. What happens in meiosis 1? How this arrest has been withdrawn? So we know the process of intra-oocyte high level of CAMP and the reduced hydrolysis of the CAMP via inhibition of CAMP phosphodiesterase. Now the question is, who is inhibiting this CAMP phosphodiesterase? From this schematic diagram, we can see that during the follicular maturation phase, FSH will bind this FSH receptor, estrogen will bind with this estrogen receptor. So there will be intracellular formation of protein kinase A. This protein kinase A will ultimately form the natriuretic peptide C, which will come out of the cell. Which cell? This is mural granulosa cell, and it will enter where? In the cumulus granulosa cell. What are those? So we know the structure of a matured Graafian follicle. The granulosa cell that is lining the wall of this follicle, they are the mural granulosa cell. Whereas the granulosa cell that is present at the cumulus efferens, they are the cumulus granulosa cell. So in the NPPC, that is natriuretic peptide C, it will be first formed at the neural granulosa cell, then it will come to the cumulus granulosa cell. It will bind with a specific receptor, and within this cell what it will do, it will enhance the secretion of cGMP. This cGMP, through the gap junction, it will come and enter into the oocyte. So within the oocyte, what is the function of this cGMP? It will inhibit this CAMP phosphodiesterase, so that the hydrolysis of CAMP will be less and the level of intraoocyte CAMP will be high, and that will cause the meiotic arrest. Now what is happening just before ovulation? Just before ovulation, the LH will bind its receptor at the mural granulosa cell as well as the cumulus granulosa cell, and ultimately in the cumulus granulosa cell, the cGMP level will be reduced. The cGMP level, it will be reduced. That's why the cGMP will not pass through the gap junction into the oocyte. If in intra oocyte cGMP level is less, so the inhibition on the CAMP phosphodiesterase will be withdrawn. It will act unopposed and it will degrade the CAMP. So that's how the CAMP level will be reduced, and there will be no phosphorylation of cyclin B and CDK1 complex, and ultimate effect is the resumption of meiosis. Resumption of meiosis. So one point is clear from here. Who is actually helping to withdraw the meiotic arrest? It is LH. It is LH surge before ovulation. So now we have reached a point where we came to know about the activity of some hormones. Now in the puberty, what is the major change that takes in the puberty? That is, during the time of puberty, the hypothalamic, pituitary and gonadal axis will get activated, and this activated axis will result in uh, synthesis of so many hormones, and these hormones are actually causing the changes during ovulation, during menstruation, formation of ovum, formation of zygotes and everything. So the puberty is very essential, very crucial. Why? Because here actually this hypothalamic pituitary gonadal axis is becoming functioning, and it has everything to do with the ovarian cycle, uterine cycle, pregnancy and everything. So we know that on about 6th day of an ovarian cycle, one primordial follicle, it will become very much active, and it will ultimately attain the stage of Graafian follicle, and the Graafian follicle, which will become this Graafian follicle, the dominant follicle. We know that the ability of the follicle to secrete the estrogen inside it will determine whether it will become dominant or not. The more estrogen that is secreted into the antrum, more estrogen secreted into the antral fluid, more will be the chance that to become the dominant follicle. Now the question arises, from where this estrogen comes. So the theca interna cell, they have the LH receptor. So LH binds with this receptor. So within the theca interna, cholesterol will be converted to androstenedione. But these cells, they do not have the enzyme aromatase. So aromatase enzyme is present in the granulosa cell. So as aromatase is absent, theca interna cannot form estrogen from this androgen or androstenedione. So androstenedione moves from the theca cell to the granulosa cell. At the granulosa cell, what happens? They have the receptor for the FSH. So when the FSH bind with this receptor, they will enhance the enzyme aromatase. So aromatase will be enhanced here, and this aromatase enzyme will convert the androstenedione to estrone, and ultimately estradiol will be formed. and it will be secreted into the antral fluid. More amount of estradiol means more chances to become the dominant follicle. Now come to the 14th day, when the dominant follicle, uh, it has achieved its diameter of 10 millimeters, so it is about to rupture, and the secondary oocyte is formed. So matured follicle will undergo rupture, and there will be release of secondary oocyte and the first polar body, and this process of rupture of ovarian wall is denoted as ovulation. Now we want to know what are the regulators of this ovulation. So primordial follicle, it is present since birth. So not from at the puberty. So its growth is not affected by gonadotropin. From the primary follicle onward, the growth will be affected by different types of gonadotropins or the hormones. And it is seen the secondary follicle, they have the FSH receptors and they secrete estrogen. This estrogen promotes the follicular. So the ovarian cycle, now we can divide it into three phases. The maturation process of follicle is a follicular phase, and after that the ovulation process, and after ovulation the luteal phase. Each of these phases, they have the interrelationship of different hormones. We want to know the different hormonal level in these individual phases. So first come to the follicular phase. In the follicular phase, there will be release of GnRH, gonadotropin releasing hormone from the hypothalamus. It will act on the anterior pituitary to release the LH and the FSH. LH will bind with the theca cell where it will form the androstenedione ion. Androstenedione will go to the granulosa cell where they will form the estrogen. One important point is here that this GnRH release is not enough. One adjective you have to add before that, the pulsatile release of GnRH. Now, if GnRH is administered by constant infusion, the GnRH receptors in anterior pituitary, it will downregulate and LH secretion declines to 0. However, if GnRH is administered episodically at a rate of 1 pulse per hour, LH secretion is stimulated. The nature and the exact location of GnRH pulse generator in the hypothalamus, it is still unsettled. However, it is known in a general way that norepinephrine and possibly epinephrine in the hypothalamus, it increases the GnRH pulse frequency. Conversely, opioid peptides such as enkephalin, beta endorphin, they reduce the frequency of GnRH pulses. Now come to the point. So we know that ultimately there will be formation of estrogen, and this estrogen has got some functions, very important function. Locally, along with the FSH, it will help the follicular growth. This estrogen will do some changes at the level of uterus. It will cause a priming of the endometrium, and in addition to that, it has some systemic role as well, some feedback mechanism as well. Now we know that the estrogen is very much important. The follicle that has the highest number of FSH receptor and the maximal aromatase activity, they produce the highest concentration of estradiol and they will become the dominant follicle. Now, at the early part of the follicular phase, there will be release of another hormone. This another hormone is the inhibin B from the granulosa cell. The main function of inhibin B is to inhibit the FSH from the anterior pituitary. But during the early part, the inhibin B level is low. That's why FSH is modestly elevated and it fosters the follicular growth. But as the estrogen level is gradually increasing, so this estrogen has a very strong negative feedback on LH. It will try to prevent the release of LH from the anterior pituitary. Now, as the follicle grows and as the estrogen concentration rises, what happens? At a certain threshold, we will find estrogen, instead of giving a negative feedback, it will give a positive feedback and try to enhance the release or secretion of LH and the FSH. We want to know what is this threshold. What is this threshold? That is, what is that particular estrogen value when the instead of negative feedback, the positive feedback will be there, and when it will occur. So it is seen that 300% increase in the estrogen concentration. That is, if the estrogen concentration it is 200 picogram per ml and it persists for 36 hours, the negative feedback will be changed to positive feedback, and it happens 36 to 48 hours before ovulation. So there will be burst of LH secretion as a result of that, and this burst is known as LH surge. So as a result of LH surge, there will be ovulation, and this ovulation will take place 9 hours after the LH peak. Now, what exactly LH does? The mechanism of this rupture, it is facilitated by LH. This LH actually enhances the secretion or synthesis of prostaglandins. This prostaglandin ultimately activates the plasminogen activator, which raises the level of plasmin. This plasmin will cause the digestion of the ovarian wall, and there will be formation of a stigma. Through this stigma or pore, the secondary oocyte and the primary first polar body will come out. Now we know that the ovum will be picked up by the fimbriated ends of the uterine tube in the oviduct, and it is transported to the uterus, and unless any fertilization occurs, it will pass through the vagina. So one point is important: if there is no fertilization, then in the metaphase arrested state, this secondary oocyte will pass through the vagina. Now our question is, what happens to the ruptured follicle in the ovary? So the follicle that ruptures, so it is promptly filled with blood, and that blood filled follicle is known as corpus hemorrhagicum. Minor bleeding from the follicle into the abdominal cavity may cause a peritoneal irritation and fleeting lower abdominal pain, which is known as milk smudge. And after that, the granulosa cell and the theca cells of the follicle, they promptly begin to proliferate, and the clotted blood inside the follicle, it will be rapidly replaced by the yellowish lipid-rich luteal cells, and it will be converted to corpus luteum. So now we know about the follicular or maturation phase of the ovarian follicles. We know the process of ovulation, and the last phase of ovarian cycle we have reached, that is our luteal phase. And we know the hormonal relationship in the previous two phases. Now we want to know what are the levels of hormones in this luteal. In the luteal phase, the most important hormone is your LH, because just before this, the LH surge has happened, ovulation has happened. Now this LH will induce the corpus luteum to release another hormone, which is a progesterone. What is the function of the progesterone? Progesterone will, just like estrogen, it will act on the uterus. It will cause the changes in the endometrium on the uterus. It will give a kind of negative feedback. So there will be reduced release of GnRH, FSH and LH. And this progesterone is very much important for the maintenance of pregnancy if the fertilization happens. Now our question is, how LH is enhancing the progesterone secretion in the luteal cell. So when the LH it binds with the LH receptor, so intracellularly again the CAMP secondary messenger level will be high, and this secondary messenger will cause the transcription of mRNA. This mRNA will enter into the rough endoplasmic reticulum that will cause the protein synthesis. This protein is nothing but an enzyme. With this enzyme will convert the cholesterol to pregnenolone at mitochondria. When this pregnenolone will enter into the smooth endoplasmic reticulum, there will be synthesis of progesterone, and this progesterone will be released into the circulation. This is how the LH is affecting the luteal cell to produce progesterone. Now we know that follicular phase, it will start from day 1 up to day 12. From 12 to 14 day, there will be the process of ovulation. Beyond the ovulation, the luteal phase will start and the corpus luteum will be formed and it will grow. How long the growth of corpus luteum will last? It is seen that from the 24th day of the ovarian cycle, the regression of corpus luteum starts, and this regression is known as physiologic luteolysis, and this process is produced by the combined effect of prostaglandin F2 alpha and endothelin 1. Now what happens if there is fertilization? We know that the ovum will be picked up, the secondary oocyte will be picked up here, and if the fertilization takes place at the ampulla, and the implantation of the blastocyst will take by 6 to 7 days. And we know that the corpus luteum, after ovulation, it persists or grows up to 10 days. Beyond 27 day, it undergoes regression. So if the blastocyst implantation occurs at 6 to 7 days, at that time the corpus luteum is growing, it is present. And if the fertilization is there, corpus luteum regression will not take place. Corpus luteum will persist. That will be denoted as corpus luteum of pregnancy. Now what is the role of this corpus luteum? It will act as a major source of progesterone. Why this progesterone is required? This progesterone will help to maintain the embryo. It will create some changes in the cervix so that embryo can be maintained. And this persistence of corpus luteum will be facilitated by the release of human chorionic gonadotrophin hormone from the placenta of the fetus. And when the placenta is good enough in amount, at that time the corpus luteum will hand over its charge of generation of progesterone to the placenta, and finally its regression will take place. So in a nutshell, we can say what are the changes of hormone in different phases. So in the follicular phase, first we look into the level of FSH and LH. You can see that this FSH, it is low level initially, and but it is higher than LH, and just before ovulation also the level of FSH is gradually increasing. In LH was almost 0, so LH level was it is almost nil, and this LH is a rate, it is almost nil. Just before ovulation the LH level is very high, and after the ovulation, during the time of luteal phase, as the estrogen progesterone level will become high, so this FSH and LH both are very less in amount. Now come to the level of estrogen and progesterone. So estrogen level, it is, you can see it is gradually, this estrogen level is gradually increasing here, and after ovulation it is reduced. There is a second peak of estrogen during the luteal phase, but that is not as high as the progesterone. So progesterone, it is totally absent in the follicular phase. After ovulation the progesterone is gradually raised. So this is all about the stages of maturation of ovarian follicle, ovulation and its regulation.